So today we're introducing pipe networks. We're going to be talking about pipe networks for the next week or two. And this is kind of a very basic introduction to it. And then we'll get into some kind of more complicated examples as we go. So our learning objectives for today. One, we're going to calculate flow rates for two pipes in parallel. We are going to list two rules for solving pipe network problems. And we're going to kind of set up and explain the theory used in what's called the Hardy-Cross method for pipe network flow problems. And I'll describe what I mean by network in a minute. But the idea is basically a branching system, a pipe that branches and has multiple inlets and outlets. And how do you determine where flow goes in that system? All right, so let's see, what are we going to do first? Let's just draw this pipe system first. So we'll start with a very basic branching pipe system. This is kind of, you could think of this as a parallel pipe system. And so we've got flow coming off into a branch, and then it comes back in somewhere downstream. And maybe we have a valve in the pipe system to, shunt flow in and out as we need. And we've got flow coming in, we've got flow coming out. And if these valves are open, then we're going to have flow entering and leaving these pipes, right? Some of it's going to go here and some of it's going to go here. We'll call this pipe A and we'll call this pipe B. And then what we're going to do is evaluate the energy equation between these 2 points, point 1 and point 2. So assume, and this is, we're just going to go over this conceptually, assume that we are given the following things. So we're going to be given the flow rate coming in, the big flow rate. We're going to be given the different lengths, right? LA, LB. We're going to be given the various diameters, DA and DB. And then of course the, roughness values. Okay. So we're basically given all the parameters that we need to know. We're given the K values for the valves, etc. So what kind of equations, take a minute to think, based on the energy equations or based on all the different things that we know, what equations can we use to figure out how much flow goes from A to B? And this is the stuff that we've covered up to this point. So Gina, since you're on top, what's one equation you think we might be able to use to solve this problem?
Sorry, the continuity of mass equation. It's like,
great. That's a great one. Okay, and what would that look like? If you kind of see this problem, we're thinking about flow going here, flow going here. How would I set that up? So I could say Q is equal to what? The big flow coming in.
Yeah, Q1 is equal to V1, or sorry, like VA AA
Right.
plus, yeah, VB.
And I'll just write it out as
Okay.
Q. So yeah,
Oh, sorry.
Q, yeah, right.
QA.
QA plus QB is in the most simplistic form. And certainly we'll need to break it down into velocities to find out the head loss, right? Okay, so yeah, this is super basic, right? We know that the flow going in is going to be equal to the split, how that flow splits among these two, or partitions among these two pipes. And that's going to be critical to solving this. Now, the other equation we could use, does someone want to venture a guess?
What about Darcy Weisbach?
Yeah, Darcy-Weisbach. So we need to know the energy loss, and that's going to influence this situation. And I'll save that one for last, but we'll use the energy equation, right? And so the energy equation, so I'll say this is equation one. Equation two, the energy equation is going to say that the energy in the energy at A, so we'll just say energy at one. So the total energy is going to be equal to the energy at two plus whatever head loss occurs in the different pipes. So we'll say head loss in A plus the head loss in B, right? So we have flow going through here, we get head loss. We have flow going through here, we get head loss. And then that head loss added up should equal the energy at point two once we follow those two pathways. Now the next thing, this is kind of a bit of a leap, is that, and I'll let you read more about it in your book, is that the head loss in pipe A is equal to the head loss in pipe B. This is a key kind of rule or property of branch pipe flow, and it's referred to as pathway independence. And the idea here is that the flow will adjust. If pipe B is really narrow or rough and there's a lot of energy loss in pipe B, then you can imagine intuitively that less flow is going to end up going through pipe B than pipe A, kind of a preferential flow path, right? And the way that works is that the flow adjusts itself such that the energy losses are equal among different pathways. And we can expand this to bigger pipe networks, and we'll do that later, to use this rule of pathway independence, and that the energy loss is the same no matter what pathway you take. And that holds for even bigger kind of branch pipe systems that might have, networks that go in and out. So the flow, essentially, if I go this way, is going to be, the energy loss is going to be the same as if I were to go this way, just as an example. So the rules then that we'll use, rules for pipe networks. First is that the sum of flows coming into a pipe network is equal to, or a point in a pipe, a branch in a pipe, is equal to the sum of the flows that are leaving that point. And you could imagine a more complicated situation like this. So we have flow going in this way, and then we could have flow leaving this way, right? And so intuitively, of course, we know that what's going in has to equal what's going out. And this is what we call the junction equation. Junction as in pipe junction, also known as conservation of mass, as Gina pointed out. And then the second rule is that between any junction, the total head loss is independent of the path and equal. along that path or along each path. And this is known as the loop equation. And it's using the energy equation, right? And it's saying that the energy equation, or the kind of the head loss, essentially using Darcy-Weisbach from across one path is equal to the Darcy-Weisbach head loss and minor losses, et cetera, across another path. And we'll see an example of a loop a little bit later. Okay, so let's look at another conceptual example and think about this a little bit more. And I'll draw a different pipe network here. So we'll just have pipe coming in, and then there's kind of a loop that meets back over here. All right, and we'll have a certain diameter over here. We'll call this D1. We'll have actually we're not going to worry about that diameter. We'll think about these diameters coming in on the branches. So we'll call this pipe A. We'll call this pipe B. We've got flow coming in, and we'll put a gate valve right here. And let's think about the overall question is, which pipe will experience more flow? And hopefully this is pretty intuitive, but we'll give you some different scenarios to consider here. So we'll say that under the first scenario, we'll say dA is equal to dB, and we'll say that the lengths are equal. But we also have that valve. So in this case, which pipe will have more flow in it? Simone, what do you think?
Well, since the head losses have to be equal, I imagine that that would be a major component of which one experiences more flow.
Mm-hmm.
Conceptually, I'm struggling to.
Okay. Yeah.
A,
well, that's
would have more head loss. So
A would have more head loss.
Is the amount of flow proportional to the amount of head loss?
Yes.
Okay.
Do you think it's going to be inversely or directly proportional?
Oh, I can't.
So let's think about it this way, and you're starting off on a great footing here, right? Thinking about the head loss. So if we're losing more energy going through pipe A because we have this minor loss right here, then one pipe is going to experience more flow than the other. We're saying that because the energy losses are different. Therefore, if we think about how energy losses manifest, in this case, we're going to be talking about major losses. So HL major is equal to FL over D V squared over 2G. If we were to think about this one only has major losses, this one has major plus minor losses, which one is going to have a greater velocity and therefore a flow rate?
Well, pathway B would have to have flow to compensate.
So yeah, so when I say head loss in A is greater than head loss in B, that's kind of like initial. This is really just this has a minor loss, right? But really these are going to adjust so that they're equal to each other. And so if we think about it, we've got a little bit of extra resistance in this flow path. And so if you think about this as resistance, this gate valve, adding on to potential additional energy loss, then the flow rate will slow down in pipe A and it will speed up in pipe B. So you're going to get a little bit more flow in pipe B a little bit higher velocity so that the major loss in pipe B is going to be equal to the major loss in pipe A plus that minor loss. So we'll do it this way. We'll say FA, LA, DA, VA squared over 2G plus K valve VA squared over 2G is going to equal the major losses over here. And by writing it this way, you can see that this velocity term, which is the same across, this velocity term is going to have to be smaller because we've got this additional minor loss coefficient for this equation to balance out. So that's how that plays out. Okay, so let's do another scenario. We'll have the same diameter, but now we'll say the length in A is less than the length in B, and we'll just leave it at that. You still have the valve in there. What do you think is going to happen in this case?
Sorry, could you say that again?
Yeah. So same diameter. The length in A is less than the length in B. So B is now longer. We'll say that LB is equal to 1.5 LA. We'll just throw that out there.
And are you asking which one will experience more flow?
Mm-hmm.
I think the shorter LA would experience more flow. There's less losses through it.
Okay, so yeah, you kind of think about initially, okay, which one's going to have more resistance? So this is LB is longer. Major losses are more important than minor losses in terms of energy loss. So if we say, okay, it's 50% longer, then that will probably override whatever minor loss we have with that gate valve. So then we'll say more flow in pipe A in this case. So because we had a longer pipe, and basically you just have a longer, kind of harder time pushing that water through. Okay, now, okay, so last one we'll do is we'll say we're going to take away, let's see here. Yeah, okay, we'll keep that valve in there. We'll say diameter A is equal to 1 foot and diameter B is equal to 0.5 feet. And Sam, since we haven't gotten to you, we'll ask you which one you think is going to have more flow. So same lengths this time and different diameters. And we'll think about this one might be a little more complicated because we know we're going to have a higher velocity probably in pipe B since it's a smaller diameter.
So, we go from a bigger diameter to a smaller diameter, but in the bigger diameter, we're going to have a smaller velocity as opposed to the one in the pipe with a smaller diameter, right?
Mm-hmm.
So, if they both have the same lengths, and the valve is still in pipe A, is that right?
Mm-hmm.
Well, let's see. Then I suppose. If the flow rates are technically the same, then I'm gonna guess will it be similar to the first case, like in terms of flow?
And are you thinking B might have more flow in it?
No, I'm thinking both of them may have the same.
Oh, they might have the same flow rate. I see what you're saying. It could be. I don't, I think you'd have to do the math, and I'm sure there's a way where you could balance the length and the diameter if they're going to be different in a way that would get you equal flow rates. You could probably, that'd be a great test question.
What have I done?
But So yeah, I mean, I think, intuitively at first glance, I would say, well, major losses are more important. The diameter features in the major loss equation. And so I would go with A as having more flow because it's a bigger diameter and you're going to have smaller losses or less losses. So hard to totally say on that, but yeah, I think you're right to kind of equilibrate on it. We'd have to probably do the math to see what happens, but I would go with A as having more flow in this particular example.
I see. So, yeah, just for most cases, okay, because yeah, it has a bigger diameter. All right, that makes sense. All right, okay.
Okay, so great discussion. Thanks for your thoughts. And now we're going to use this same example, and we're going to put some numbers to it and do a calculation together. Clean up that board right there. Okay, so here's our example we're still going to work with here. And I'm going to start giving you some actual values for these different pipes. We're going to take that valve out, just going to simplify things. Okay. So we'll say that we're going to evaluate the energy equation between these 2 points. So before the flow splits and then after it converges. And we're going to say that the length at A is, and in pipe A is 10 feet. So this is length A. And then we're going to say the diameter is 1, length B, 10 feet. And hey, this is that exact example, so we get to do it together. 0.5 feet is our diameter in B. Same pipe material, so we'll say that roughness is 0.00085 feet. And then we'll just go ahead and calculate some stuff together. We will do the area. We'll do the relative roughness. And then we'll go back to the area over here. Relative roughness for this pipe. All right. And what else are we going to do? Yeah, that's all the information we need right now. So we can set up those 2 equations and solve them. Some is not going to be too painful. So let's go ahead and do that. And ultimately, we're trying to solve for, I guess just to write that up here. So what is the flow rate in pipes A and B? How is that flow partitioned? Hang on a sec, guys. So the first thing we're going to do is the junction equation. And that was our conservation of mass. And so that just says QA plus QB is equal to whatever the big Q is. And I didn't write that up. So the Q coming in is equal to 10 cubic feet per second. All right. So that's a good one to have in our back pocket. And then let's write out the loop equation. The loop equation is just saying that whatever pathway you take, you're going to have the same energy loss. And we're keeping it simple. We're not doing minor losses, just major losses. So head loss, depending on which path you go, is equal to the major losses. So FA, LA, DA, VA squared over 2G. And that it should be equal to the major losses through pipe B. All right. Now we've got two equations, and we'll note that velocity of A is in this equation, and velocity of B is in this equation. And so ultimately, we are going to be solving for velocity A and B. So two equations, two unknowns, not super duper hard, but we could have an iteration here, right? Because how do we know what F value to use? How would we start with an F value for this problem? What's an assumption we typically make?
We're at fully turbulent flow. Is that right?
Yeah. So start with fully turbulent assumption. Turbulent. And that's typically Reynolds number is equal to 10 to the 8th for pipe flow. So you could plug that into the Swami-Jain equation. You could go to Moody with your relative roughness, and you can get an F value for that. Now we could do this where we plug that F value in, we solve for velocity A and velocity B, and then we iterate, right, and calculate our Reynolds number again, calculate our F value again. That would be the proper way to do it. And fortunately, we have software that will do those iterations for us. EPA Net does that. So for now, we're just gonna, for this problem, we're just gonna assume that we're not gonna do that. And we're gonna do our friction factor A is about 0.019. And then our friction factor for pipe B is about 0.0225. And then we'll just move ahead with that. All right, now we need to solve all this stuff. Instead of solving for velocity, though, we're gonna actually solve it for discharge. And so we're gonna put Q in for velocity of A, and we're gonna put QB in for velocity of B. And so we'll note that velocity squared is equal to, let's see here, Q over A squared. And then we'll note that Q over A, and so area is equal to pi d squared over 4 squared. And so then we get 16 Q over pi squared d to the 4th. So that is the big thing that we're going to plug into the Darcy-Weisbach equation. We're going to divide by 2, right? Because you got that 2g in the denominator. And so what you end up with for both sides is you end up with 8 up top, friction factor, length, Q squared, divided by pi squared g, and then diameter to the 5th, because we already had a diameter down there. Okay, and then that's going to equal, on the other side, 8 FB L B Q B squared all over pi squared G dB to the 5th. All right, we get to cross a lot of stuff out, makes life easy. So all those constants are crossed out. So we end up with that. And then we also have our, okay, what we'll do is, before we get down to the junction equation, is that we'll plug numbers in here, and then we'll kind of factor everything out. So up top, we get, oh yeah, sorry, the lengths were the same too. So we get to cross those out. Boom, boom. Okay, life's really easy. All right, it's not just friction factor, so 0.019 QA squared all over our diameter, 1 foot to the 5th. And then we have our friction factor, 0.0225 QB squared all over 0.5 to the fifth.
I got a quick question about the lengths.
Uh-huh.
So yeah, so in this case, yeah, they are the same, but if they were different lengths, like for a different type of problem, yeah, would we not be able to cancel them out then, right?
Right, and because for these problems, you're given a pipe network and you're solving for Q. So by being given the pipe network, you're going to have all those lengths that you need.
Gotcha.
Typically, it's like the diameters and the lengths are prescribed, and now you're just trying to figure out how the flow is partitioned through the network.
Yep.
So that's typically going to be given. There might be a problem where you have to solve for length, but okay. So now we can kind of simplify and factor, and what we end up with is QA squared is equal to 37.9 QB squared. And then we can just take it down to QA is equal to 6.16 QB. So now we've got that pretty simple equation from the loop equation, and we can now bring that back to the junction equation, which said that QA plus QB is equal to 10 cubic feet per second. So we'll plug that in for QA, and we'll say 6.16 QB plus QB is equal to 10 cubic feet per second. And then we can solve for QA and QB. So QB ends up being 1.4 CFS, and QA ends up being 8.6. Quite a difference there, right? Non-linear difference, right? Because we got that non-linear Darcy-Weisbach equation where velocity is squared. And then we can solve for velocity, and we get velocity B is equal to 7 feet per second, and velocity A is equal to 11 feet per second. So we get a lot more flow able to go through that diameter that's 1 foot versus half a foot. Quite a big difference, right? This is factor of 5 or so difference between the two, 6, just with that half, that diameter reduced by half. So quite a big difference.